In this video, we're going to continue with factoring and focus on special binomials. So binomials are two terms, and there are two different kind of special types here. The first, which is the most common, is the difference. This should be an E here. That's just an E. Difference of two squares. So when you have an example, you have a square minus a square. So for instance, something like factor x squared minus 25. So you want to recognize that this is a special case. It's only two terms, right? Not the three or the four that we've kind of been used to seeing. And each of those is a square, right? X squared is a square, obviously, and then 25 is a square because that's 5 times 5. So what happens in a special case like this is that when you factor, yes, you can go through trial and error, or yes, you can go through grouping. But what you want to notice here is it's very particular. They have doubles, but the signs are different here. To get negative 25 would be a -5 and a +5. So the factorization is always going to be pretty straightforward. You're going to take that square root of the first part, the square root of the second part, and you're going to use the opposite signs. Okay? It doesn't matter if you put the minus first and the plus second, it's going to work out. And I'll show you that this does actually check out, right? So if you multiply this through, you have x squared minus 5x plus 5x minus 25. So what ends up happening is those middle terms cancel each other out. You get a 0. And that's why you have the plus and the minus. So you get that canceling in the middle. Excuse me. And then you have your final answer here of just x plus 5, x minus 5. And this is a pretty common thing to see. So it's definitely an example you want to watch out for. All right, let's do another example. All right, so this one's a little bit different. And if you look at it, you're probably saying, okay, Professor Pollard, that is not a perfect square. 8 and 18 are not perfect squares. But remember, whenever you're factoring, the first thing you should do is look for a GCF. This one didn't have anything here besides 1, but my GCF does exist here. There is a GCF of 2. So the first thing I'm going to do is take that GCF out. And then I'm left with 4x squared minus 9. And now, hopefully, you're recognizing that 4 is a perfect square, and so is 9. So the whole thing was not, were not squares, but once we took the GCF out, we can now apply this different technique here. So for this part right here, when we factor, again, you're going to use the square roots. So the square root of 4 is 2, so this will be 2x. And the square root of 9 is 3. And then what you're going to do is use a plus and a minus, and that will get that canceling in the middle. Be careful, you do have to have a minus sign here for this to work. This is the difference, so subtraction of two squares. And then what you can do is just bring that outside GCF down, and we have our final answer. Now here's one again that looks a little bit different. You may not recognize this right away as two squares. Hopefully the 81 is jumping out at you because that's 9 squared, right? 9 times 9. But this is also a square because x to the 4th is x squared times x squared. So it's x squared squared. So you get that same repeat factor here, just like you do that 81, that 9 and 9, obviously one positive, one negative, but you get those repeat factors there. So you do have a perfect square in each case here. And as we factor it, then it's going to be x squared, 9 and 9, and then of course, one positive, one negative, right? Because you do need to have that minus sign in the middle. Now this one's a little bit different again. My last two examples, there weren't any squares or cubes left over. But here I do have squares or cubes, and I can see right here, this is also the difference of two squares, right? X times x 3 times 3. So this piece can actually be factored again, xx, 3, 3, plus and minus. But I will tell you now that you cannot factor the sum of two squares. We say that that is prime. So polynomials that cannot be factored are prime, and they do exist in all cases. So sometimes we just can't factor something. And anytime you have the sum of two squares, it can never be factored. So that's just going to come straight down here. And this would be my final answer. Now, there's another technique as well that is common with binomials, although this is the most common for binomials if you see it. And actually, I'm just going to go to the next page. I think that'll be a little bit easier. And this is going to be the sum or difference. I keep writing my E's funny. Difference of two cubes. So instead of being squares, we're talking about cubes here. So there's two different formulas depending if it's a sum or difference. So the sum looks like this. And then the difference formula looks like this. Now, this is one of those rare examples where I really do recommend you use the formula. I don't have a trial and error method or anything else to do for something like this. So you really do want to use the formula here, and I'll show you how it works. All right, so let's do a simple example first. Factor x cubed plus 8. So again, when you see binomials, try to think, does this match anything that I know that's special? And this one does. You actually have two cubes here, right? Because this is x cubed, but 8 is actually 2 cubed. So what's happening in the formula here is that your a cubed is the same thing as x cubed, and your b cubed here is the 8, right? So that's your a cubed and that's your b cubed. So what this means is that your a is just the x, and your b value is just the 2. It's the cubed root of them, right? That base value that's being multiplied. So what you're going to do is just take the formula and substitute in x and 2 here for a and b. So my formula for the sum, right? So the sum is that top one. And I'm not going to lie, I don't have these memorized. This is something that I would just put on a note card and kind of keep near me as I'm doing these questions. So wherever I see an a, I'm going to put an x. And whenever I see a b, I'm going to put a 2 here. So this would be x squared minus x times 2 plus 2 squared. And then I'm going to simplify it one more time. So here I'll write that as minus 2x, and 2 squared is 4. Now this cannot be simplified anymore. So I know it still has a square in it, but this is as broken down as this formula gets. So that is your final result there. And again, in all cases, you would still look for a GCF first. I know I'm kind of glossing over that sometimes, but you would look for a GCF first with any single problem that you're doing. Here, I don't have any GCF. And again, you see that binomial, hopefully something is jumping out at you that this is a little bit different, particularly where I see a cube here. So what I can do is think about my cubes. Are these cubes? Well, 64 is, that is 4 cubed. And 125 also is, that's 5 cubed. So what's happening here is that your a cubed is that 64x cubed. So your a value is just 4x, just taking that x down to the base form. And your b cubed is that 125. So your b value here is just 5. This is the subtraction version. So I'm just going to copy down my subtraction formula here. And then I'm just going to plug in my A and my B values right where I see the letters in the formula. Now I am using parentheses when I plug in that 4x because when I square it, I do have to square the whole thing. So I'm going to simplify here. So 4x squared, I square both parts. So that would be 16x squared. Here, 4 times 5 is 20, so 20x. And then 5 squared is 25. And again, these are going to be broken down as far as they can go. So you don't have to worry about checking or anything like that. That's going to be your final result. All right, so when you see binomials, not everyone is going to be special, but a lot of times they are, at least for homework purposes. So look through, see if they do look like perfect squares or perfect cubes. And then if they are, then you know you have a special way that you can factor those, typically using a formula.